Welcome back. Today we're going to finally start talking about manifolds. They're pretty important because they're an interesting class of topological spaces, and compared to the usual hot garbage we tend to see, they're actually very well behaved. Here's the definition of a manifold. It's a topological space that is second countable, Hausdorff, and every point has a neighborhood homeomorphic to an open set in Rn. If you don't remember any of those words, do the YouTube thing and click the cards here, or there will be links in the description. Really, we tend to sweep second countable and Hausdorff under the rug, because second countable is just a finiteness condition, and Hausdorff is a sanity check condition. So really, when someone says manifold, my mind just jumps to the every point has a neighborhood homeomorphic to an open set in Rn part. Although, it really doesn't even do that. My mind just thinks like Rn, or if my monkey brain is a little bit more evolved, then I think I can cover my space with an atlas of charts that are Rn's. Okay, what are atlases and charts? When we say every point has a neighborhood locally homeomorphic to Rn, then a chart is just the open subset and the homeomorphism. An atlas is just all of the charts. In other words, the charts cover the manifold. Hang on a second. Remember that compact topological spaces are also defined via a cover of open sets. I'm not making a connection between compactness and manifolds right now. Manifolds may or may not be compact. I'm making a connection between the idea of covering your topological space. That's kind of cool. Maybe we should do it more often. This whole digression is really just for my benefit so that I can say I told you so when we get to schemes and growth of deep topologies. One remark is that when we cover a manifold with charts that are homeomorphic to Rn, then it's the same n everywhere. So we say that the manifold is of dimension n, or that it's an n-manifold if we're feeling froggy. So if we want to cook up some examples, and given a new definition we always do, then we first fix an n and ask for an example of an n-manifold. So let n be 1. What are the 1 manifolds? Well, here's a dumb example. How about R itself? Certainly, we could have an atlas with one chart that is just all of R. Or to say it in that monkey brain language, R is like R. So a line is a 1 manifold. But there is another. Any guesses? Pause and give me your answers in the comments. I'll wait. Actually, I won't wait because I just told you to pause. So, that's right, it's a circle, S1. We certainly believe that a circle is one-dimensional, but if we want to prove that S1 is a 1 manifold, then we need to cook up the atlas and charts. There are many, but any one atlas will do. So we can give an atlas with 2 charts. The first chart is R homeomorphic to the circle minus the top point, and the second chart is R homeomorphic to the circle minus the bottom point. It's okay that our charts overlap, as long as every point is covered. As you perhaps might have guessed, this example completely generalizes. Of course, Rn is an n-manifold. Rn is like Rn. And the n-dimensional sphere Sn is also an n-manifold because it's the one-point compactification of Rn. So it's really easy to build a chart. The n-sphere minus 1 point is homeomorphic to Rn, and then you just add one more chart by throwing away a different point to cover the entire n-sphere. For example, S2 minus the North Pole and S2 minus the South Pole is an atlas that demonstrates that S2 is a 2 manifold. Up to some technicalities, lines and circles are the only 1 manifolds. But in 2 dimensions, we do get more than just planes and spheres. We've actually seen some different examples before when we started talking about gluing polygons. We glued the sides of a square in different ways to get things like donuts and real projective planes, and both of those are examples of 2 manifolds. At the time, we called those surfaces, and that's just another name for a 2 manifold. It's easy to see that the donut or RP2 are 2 manifolds, because you just have to give me an atlas of charts on the square, such that I still have an atlas even once I glue the sides together. In other words, even after gluing, you still have charts which are homeomorphic to R2. It's perhaps easier to visualize that you can do this on the donut, so here's a heuristic to let you know that it's possible. If you build the donut by gluing the sides of the square, but then in the donut you don't indicate where those seams are, then there's no way to see where the sides of the square are. In fact, every point on the donut looks like every other point. So if I can put a chart on the donut in the middle of the square, then I can put a chart on the donut along the edge of a square after gluing, because in the donut visualization, those points are completely indistinguishable. Also, I'm starting to feel like a big baby because I keep calling this space a donut. I think we've graduated to calling it a torus. And I've mentioned before that all connected, compact, and boundaryless 2 manifolds, and there are a lot of them, come from gluing sides of polygons. And furthermore, come from gluing those polygons in very fixed ways. That statement is called the classification of surfaces. You know, last time we mentioned the classification of surfaces, we didn't know everything we needed to prove it. But I think we know all the words now, and the proof itself is pretty elementary. And another time. So, thus far, we've defined manifolds, and we have some examples under our belt. You can also cook up some non-examples. Anything that's not second countable or Hausdorff fails to be a manifold for silly reasons. Such spaces are basically a bit too wild for us to want to include them in our definition. So for example, an uncountable disjoint union of R's is not a manifold, because it's not second countable. Or a line with two origins is not a manifold, because it's not Hausdorff. Those do both feel relatively like R-ish, but we don't want to consider them as manifolds. And then of course, anything that fails to be locally Euclidean is not an n-manifold either. We've seen plenty of different topologies, so feel free to take your pick there. We have one more thing to square off for today. So a few moments ago, when we showed that the circle S1 is a one-manifold, I blithely said that circles are one-dimensional, and so it ought to be a one-manifold. Maybe some of us took issue with that? Wait, Eric, I can hear you say. A circle is one-dimensional? But if something is one-dimensional, that means it's flat. I can only go in one direction, forwards or backwards. But I can go in two directions in a circle, left or right, and up or down. Okay, so honey, first of all, you're thinking of a disk, not a circle. I'm sorry your kindergarten class lied to you. It's okay though, we all thought this at one point. It's a rite of passage to be snarkily proven wrong by a mathematician about this. It happened to me and now it's happening to you. So, a disk is the shape that you color in. A circle is just the frame, just the boundary of the disk. And yes, the circle is one-dimensional. I can only walk ever forwards or backwards along the circle, only clockwise or counterclockwise. That's just one direction. If I want to be a bit more precise, then I can say I only need one coordinate to say where I am on the circle, my angle measure. But this distinction raises an important point. Sure, a circle S1 might be one-dimensional, but we draw it on the plane, R2. I can't draw a circle without two dimensions, even though the circle itself is one-dimensional. This leads to the concept of an embedding. Here's the definition. Say I have a map F from X to Y. We say that F is an embedding if it is a homeomorphism onto its image. In other words, F sends X to some subset of Y, call it F of X. If X is homeomorphic to F of X, then F is an embedding. One note, to do this, F needs to be injective. It needs to send every point in X to a unique Y value. So how does the idea of an embedding describe drawing the circle in the plane? Well, the circle is an abstract topological space. Visualize it as its own thing, untethered to the way we draw it or anything like that. I'd animate an example on screen for you, but of course I can't show you a circle without drawing it on the plane. Now, consider the function f from S1 to R2 that takes an angle measure theta, which we said is all that you need to tell me a point on the circle, and plots the point cosine of theta, comma sine of theta on the plane. If that sounds a bit too abstract right now, just keep this in mind. All the function f is doing is taking that abstract void circle and drawing it in the plane. This function is an embedding. It's injective, the circle doesn't overlap itself anywhere, and it's a homeomorphism. Not between S1 and R2, of course not, but between S1 in the void and S1 on the plane. In other words, it's a homeomorphism onto its image. It's an embedding. We now ask the natural question, which demands itself to be asked by the laws of the universe. There ain't nothing special about the circle. Can every manifold be embedded? Well, that's a sloppy natural question. Certainly every manifold can be embedded in something. Every topological space is homeomorphic to itself, so every manifold could be embedded into itself. That's not what we meant to ask. There ain't nothing special about drawing the circle. Can every manifold be embedded in the plane? Well, no, of course not. R3 is a 3-manifold, and I can't embed R3 into R2. We won't be injective. There's no way to take 3 dimensions and squish them into 2. That can't be what we meant to ask either. There ain't nothing special about the circle being 1-dimensional and the plane being 2-dimensional. Can every n-manifold be embedded in Rn+1? Now we're getting somewhere. This still isn't the right question to ask, because the answer turns out to be no. But it's not nearly as easy to see why. I could just claim an example for you. The Klein bottle, good grief, it is covered in chalk, is a 2-manifold because we can build it by gluing the sides of the square. but we can't embed the Klein bottle into R3. You might ask, wait, Eric, I can hear you say, your room seems pretty three-dimensional to me, and you're holding a Klein bottle. But this isn't an embedding of a Klein bottle. There's some self-intersection right here. So the map from the abstract void Klein bottle out there to the one that I'm holding right here isn't an injection. But note that this doesn't prove that it's impossible to embed the Klein bottle in R3, just that this way in particular isn't going to do it. But it is impossible. No matter how you try, you can't embed the Klein bottle in R3. Here's a very bad proof. If it were possible, then Cliff Stoll would have done it for me when I bought this. Okay, so what the hell is our supposedly natural question supposed to be? There ain't nothing special about embedding an n-manifold into Euclidean space. Can every n-manifold be embedded into some Rm? Now we're talking. We whittled the question down so far that it's no longer easily false. That must mean it's true, right? That's how math works, right? The answer does turn out to be yes. Every n-manifold can be embedded into some Rm. The proof, at least for compact n-manifolds, is not too hard. The idea is to cover your manifold and build something called a partition of unity on it. Then you define a candidate embedding function in terms of this partition of unity, and then verify that it is indeed an embedding. Ta-da! We could take the time to go through that in detail. Like I said, it's not too hard, but the proof itself I don't find as valuable as just the fact that it's true. In particular, via this proof, the dimension of Rm ends up being pretty big, because the proof makes sure that your topological space is nice and roomy in Rm, so that there's no self-intersections. But in specific cases, you can often do a lot better than what the theorem might suggest, and embed certain manifolds into smaller dimensional spaces. Here, just to give you a taste, the proof I have in mind would say that you can embed the circle into R4. I mean, that's obviously true, but it's also obvious that we could do a lot better. But that's the best that the proof could have done for us. So that just about does it for manifolds and embeddings. We'll see both manifolds and embeddings show up pretty often, so they'll start to feel like familiar friends. Except for RP2. We don't trust non-orientable manifolds around these parts.